So, we were discussing about hypothesis testing in the context of multiple linear regression model, right. And so far we have discussed testing three types of hypothesis here. First one was the first hypothesis that we were testing was basically the marginal contribution of an explanatory variable. That means, when you know that one variable is already there in the model, if I add an additional explanatory variable, then what would be the additional contribution of that variable in the explanatory power of the model. And I will just quickly recap that model and for your own for your understanding, then I will be using the same data and I will estimate the model, and I will also show you how to conduct that hypothesis testing. So, here we are interested in child mortality rate as a function of female literacy rate and PGNP, as you know. So, let us say that our initial model is CM equals to alpha plus beta 1 FLR plus beta 1 FLR plus UI and we call this model as old, and from estimating this model we will get, let us say, R square old, and then when we add the PGNP variable in the model, then that will become CM equals to alpha plus beta 1 FLR plus beta 2 PGNP, per capita GNP plus UI, and if you estimate this model, you will get another R square, which is, let us say, R square nu, right. And then how we have defined our F statistic? We define F statistic as R square nu minus R square old divided by number of new explanatory variable or number of new explanatory variable added in the model, which is 1 here, which is 1 divided by 1 minus R square nu divided by n minus k, where k is the total number of parameters to be estimated in the new model, right. K is the total number of parameters to be estimated from the new model. Now, we will estimate the model and we will put the values of R square new, R square old, n and k in this function, then we will get the calculated value of f, right, calculated value of f. Okay. So, I will now show you how to estimate the model. So, here what you have to do, just I will run the first model reg CM on FLR, okay, reg CM on FLR, and if you look at the R square value is 0.6696. So, after this I will run the complete model, which is a reg CM FLR and then PGNP, and this would become your complete model or the new model, and you will get the R square nu as 0.70. Okay. So, what I have to do, Now, you have to use this 2r square value and put it into the function, okay, what we have defined earlier. All right. So, that means you have to say that here this would become 0.70 minus 0.66 divided by 1 into 1 minus 0.70 divided by what is your n? N is actually, if you look at, your total number of observation is 64 and total number of parameters to be estimated from the model is 3. So, 64 minus 3 is 61, right. So, here I will put n minus k, that means 64 minus 3 is 61, okay, 61, all right. So, once you do that, you will get the calculated value of f, and that calculated value of f you have to compare with the tabulated value of f, which is available at the end of your textbook, okay, for a specific level of alpha equals to, let us say, 1%, 5% or 10%. So, you can easily calculate. So, this would become your f, I will write f which is calculated, and then you have to compare this calculated f with the tabulated f, and if this is greater than f tabulated, then what we will do? Your calculated value is greater than the tabulated value, you have to reject your null, reject your H naught. And what was your H naught? If you remember, our H naught was, just one second, r square nu equals to r square old. So, that means there is no significant difference between the new r square and the old r square. So, alternatively we can say that the new explanatory variable which is added in the model has insignificant explanatory power, okay. And if the f calculated is less than f tabulated, then what would be your decision? Do not reject the null, do not reject the null. Do not reject null, okay. This should be your decision, all right. So, you have to calculate the f value and compare this with the tabulated one. This is how you can test the hypothesis whether r square nu equals to r square old, okay. So, that means you can justify adding the new variable PGNP in the model if and only if you can reject this null hypothesis. That means r square nu equals to r square old, you have to reject, okay. You have to reject this null hypothesis, then only you can establish that yes, the new variable PGNP has significant explanatory power. So, this was the first hypothesis we tested yesterday, we are talking about. And what was your second hypothesis? Second hypothesis that we were testing in the context of a production function, or here in this context also you can check it, when your model was Cm equals to alpha plus beta 1 FLR plus beta 2 PGNP plus UI. So, what was the second hypothesis we are testing? Second hypothesis is a equality between two regression coefficient, that is our second hypothesis, equality between two regression coefficients. So, that means our null hypothesis here we were testing beta 1 equals to beta 2. Okay. That is our null hypothesis that we are going to test, all right. And then how we are testing? How we have constructed the test statistic? The test statistic T, so this can be alternatively written as H naught beta 1 minus beta 2 equals to 0. And how we are defined T? T was defined as beta 1 hat minus beta 2 hat, okay, beta 2 hat minus 0 actually divided by standard error of beta 1 hat minus beta 2 hat. Okay. And what is standard error of beta 1 hat? That is basically square root of variance of beta 1 hat plus variance of beta 2 hat minus 2 covariance of beta 1 and beta 2, right. So, that means this can be written as beta 1 hat minus beta 2 hat divided by variance of beta 1 hat plus variance of beta 2 hat minus 2 into covariance of beta 1 hat beta 2 hat. This is how you have to calculate your T. Now, once again what you have to do, this calculated T, what is your decision? How will you take your decision? If T calculated is greater than T tabulated, then that implies that you have to reject your null, reject your H naught. Okay. So, this will give you T calculated value and you have to check the tabulated T at a specific level of alpha, either 1%, 5% or 10%. Then depending on the value of T tabulated, you can easily decide whether to reject your null hypothesis or not, right. And if T calculated is less than T tabulated, then what would be your decision? Do not reject your null, do not reject your H naught. So, this is the simple rule of decision rule of your hypothesis testing. Now, from this model what I will do, I will now show you how to implement this particular hypothesis testing using the software. Okay. So, I have already run the complete model. So, from here see I have everything. So, variance of beta 1 hat, variance of beta 2 hat, you have standard error. So, if you square it up, that will give you variance of beta 1 hat, that means variance of this FLR, variance of beta 2 hat which is nothing but square of this, okay, square of this, and then you have to take 2 into covariance of this and this. Now, only covariance part is not given here, that you have to additionally get, and for that we will be using a specific Stata command, and you have to remember the command for getting the covariance for this two variable FLR and PGNP coefficient. And what is that command? The command is estat VCE. So, immediately after running the complete model, if you put this estat VCE command, then that will give you this type of result. Look at this. This is called the variance covariance matrix, and from here what you have to look at, this PGNP and FLR, this is the covariance. This is the covariance 0.000001. So, minus 0001 is basically the covariance of FLR and PGNP. Okay. So, this you have to put it into the formula. So, that means from here I will take square root of this, then square root of this plus 2 into this value, 2 into this value. Okay. So, what I will do, square root of, so that means this formula will become, this formula will become this formula. So, that means beta 1 hat minus beta 2 hat in the numerator, and that is beta 1 hat is basically minus 2.23 minus 2.23, then again minus of this. So, it will become plus 0.005. So, minus 2.23 plus 0.005, I think that is the value 0.005, yeah, and then divided by 0.20 square, 0.20 whole square plus 0.002 square, 0.002 square plus 2 into sorry, this is minus actually, minus 2 into what is the value you got there, covariance is minus 0001. Okay. So, we have one minus here, and if you put minus 0.0001, this is how you have to calculate your t, and this calculated t should be compared the tabulated value of t at a specific level of significance, alpha equals to 1%, 5% or 10%. So, this is our second hypothesis, wherein we were testing about the equality between two regression coefficients, right, two regression coefficients. And then we have discussed our third hypothesis, that is basically, what is your third hypothesis? Third hypothesis we are testing about, the third hypothesis that we are testing, that was testing the validity of linear restriction. So, please remember what we are testing, testing validity of linear restriction. So, this particular linear restriction we can discuss in the context of a production function, that would be better, it would be more meaningful. So, what I will do, I will take you to the production function that we are discussing yesterday. The production function what we are discussing was yi equals to beta 0, then beta 0, it was beta 0 into x1I to the power beta 1, then x2I to the power beta 2 into e to the power ui. Okay. And after linearization, so this is the production function, and after linearization what we got, log, if you take log of both side, log yi equals to log of beta 0 plus beta 1 log x1 plus beta 2 log x2 plus ui. Okay, ui. This is our linearized production function, and where we said that x1 equals to labor and x2 is capital. How we have defined here? x1 equals to labor, 2 factors of production, and x2 equals to capital. So, these are the 2 factors of production we are using in the production function. Okay. And then we also said that since this is a linearized model, log-log model, in this log-log model, the interpretation of beta 1 and beta 2 is actually the direct elasticity measure. So, that means for 1% change in labor, what would be the change in your output, and beta 2 indicates for 1% change in capital, what would be the change in output. Okay. So, that means I can interpret beta 1 as, okay, when labor changes by 1%, okay, 1%, then output changes by beta 1%, direct elasticity measure. Okay, direct elasticity measure, and we have also denoted beta 1 as returns to labor, okay, returns to labor, and then beta 2, sorry, this is beta 2, how we have defined, what would be the interpretation? That means for 1% change, in capital, output changes by beta 2%. Okay. But please do not forget to mention on an average and keeping the impact of other factor constant. So, that means when I am saying that interpretation of beta 1, when labor changes by 1%, output changes by beta 1%, keeping capital constant. Similarly, when capital changes by 1%, on an average output changes by beta 2%, keeping labor constant. That means I am not changing labor when I am changing capital, and these two are, when you keep the other factor constant, we said that is basically returns to factor, and when both the factors changes by 1%, then the relevant concept is returns to scale, right. So, that means we said that beta 1 plus beta 2 basically indicate returns to scale, okay, returns to scale. And what we are testing? Our claim is that this particular production function, let us say, exhibit either increasing returns to scale or diminishing returns to scale. That is our claim. And if you nullify your claim, then your hypothesis, null hypothesis would be beta 1 plus beta 2 equals to 1. This is your null hypothesis. And alternative hypothesis would be, what would be your alternative hypothesis? Alternative hypothesis would be beta 1 plus beta 2 not equals to 1. So, that means this consists of two things. It can be either greater than 1. In that case, we will say that production function exhibits increasing returns to scale. It can be less than 1 also, and in that case, we will say that production function exhibits diminishing returns to scale, okay, diminishing returns to scale. And how we have formulated the test statistic here? The test statistic was formulated as, how you have defined our T? So, when this is your null hypothesis, we can say that T was defined as beta 1 hat plus beta 2 hat minus 1 divided by standard error of this, standard error of beta 1 hat plus beta 2 hat. Okay.